Hi, hello everyone. I'm here and also here. And today I'm gonna be going over the quiz. And the setup is gonna be that I'm gonna have the quiz in my tablet. It's right here. And I'm going to be solving it in my tablet while I'm talking to you and reading from my computer over here. So yeah, let's start. Let me start sharing my screen. And doing that right now. Share screen. Okay. So, okay, this is a quiz that we have. So let me go and also like starting. So we have um first bar that you have to read and sign. We won't be going over that today, but let's start with the problem, which is the fun part. All right. So in the pharmaceutical industry, we have something called fill and finish, also referred as fill finish. Refers to a final stage in the manufacturing process where pharmaceuticals are filled into containers, such as vials or syringes, and sealed to distribution and use. It ensures the proper dosage and integrity of the product before reaching the end user. So from this, so far, we know that we have a container, and that container is receiving some stuff, and it's called fill and finish. So we have this, and then the container, our lovely container. Sorry, I'm not an artist. It's going to have the whatever we were putting inside. Awesome. So let's continue. Let's continue reading. You join the manufacturing team as a fill finish engineer, and you're assigned the filling station for insulin. Okay, it's going to be important. So let's write it. The station consists of a high capacity device designed for efficiency. This device receives an insulin formulation from one input. Okay, so we have something like an input stream. Input. I love to do this kind of thing. So usually when I'm reading and start writing, even though probably they're gonna ask for me to do drawings later, but yeah, I'd like to picture what I'm getting. Input, and we have insulin. Okay, let's continue reading. So this is stream one, awesome. And it splits that formulation to three vials, okay, simultaneously. So we have some input, some device. In this case, it should be like the filling uh, like machine, and then we have three outputs, correct? Splits that formulation into three vials simultaneously. To streamline manufacturing production process and avoid unnecessary stoppage cleaning time, this device must be run at steady state. That's super important. Let's highlight that. That's this something that we know there's going to be a assumption that we're going to use. So here we won't have a change. Whatever is in the system is going to stay in the system. Let's say X amount of mass is going to be in the system at all times. In this case, it might be insulin, it might be another stuff that they're going to talk about later in the problem. You're tasked with helping the team. You're tasked with helping the team monitor the performance of this device. Okay, so we're performing this machine. Ooh, I love to make. There you go. Okay, so we got to monitor that machine. Okay, so we have the velocity of stream one, the diameter, stream one, the diameter of three filling syringes are identical. Hey, that's important because saying that it's identical and also saying that it somewhere here it says that it splits, that means that whatever we're getting in the like the first stream, sorry for the noise, I'm in Barcelona right now, people are like screaming. Uh, it's gonna be split into three streams which are the same length, which means that intuitively we know that the mass of those streams are going to be equal, or the addition of that mass, output mass, is going to be the same as the input. So we have this three streams, whatever this is, like stream 2, 3, and 4, whatever mass 1 is going to be equal to mass 2 plus mass 3 plus mass 4. So because that's a conservation of Mass. Okay, let's continue. I haven't done anything yet, but I just wanted to talk over the questions so you know intuitively what to do. We also know, oh, awesome. We know that the process happens relatively quickly, and the result, the insulin is not degraded. So there's not this right away is telling us no generation, no consumption. So yeah, we're not getting more or less insulin, and that's good. Great. And we're getting density. That's gonna play out later. I'm gonna pause here for a second, and I remind you everyone to make use of something that is in Canvas, which is I have here at the end, which is this equations. They're relatively simple. I'm pretty sure you can like memorize them all, but I would definitely, if you can, while you're doing your homework, have it by your side and be able to look at them and not mess something up, because it's, at least for me, something that happens relatively easily. Let's go back to a problem. So draw the diagram. Okay. So let me draw the diagram. So we get our box. Oh, no, I didn't want to do that. Let's see now. Better. There you go. Okay, we have a box and we have an incoming input stream called stream one. And we have we know a lot of stuff. So we know that the stream one, the velocity is 50 centimeters over second. We know that right off the bat. We also know the diameter. So whatever this tube is, and that's going to be helpful for the area that we're going to calculate later on. So write that down. Diameter 1 is equal to 2 millimeters. Okay. Then the diameter of the 3 filling syringes is identical, equal to 5 millimeters. Okay. So for this, and this, which are streams 2, 3, and 4, we know that their diameter is 5. Let's see, diameter 2, diameter 3, diameter 4, 5 millimeters, 5 millimeters, 5 millimeters. Awesome. Let's see, what else do we have? No degrader or consume. Awesome. And this information is constant. Okay. And let me just make sure. We have something that I forgot doing. I forgot to do here. I'm gonna erase this because it could be thought that I'm talking that that's the boundary, but it's not. It's that we have to create a boundary. So this our boundary, we should like note it. Boundary. Okay. And the surrounding, it's not something that you have to do, but I will do it because it's common practice, or it can help you clarify what exactly you're looking at. We can do the rest of the universe. Okay. And I forgot to state that this is a system looking at. Okay. That's it. Awesome. So let's continue. So we label the system, we label the surroundings, and we did the boundary. Good. And we added information that we gathered from here. You can also say that the density is equal to 1.2 grams over milliliter. What sensory property are you tracking in this system? So let's go back here. So we have this machine, right? And we are getting like, okay, this machine is like getting some here. So what we have in our system, and we're at the end of the day filling, it's insulin. So what it would make sense here is to track the insulin mass. So I'm gonna go right there and say mass of insulin. Yeah, that's what I'm gonna be tracking, which makes sense, at least from what the problem is saying. So I'm gonna go for that. What assumptions are you making about the system? Okay, so we're talking about them. So the first one that we can make right away is this one, steady state, okay? And because, I mean, actual problem states, so steady state. Additionally, we had another one. Okay, no generation or consumption, okay? So, but what is another way to say that? Hmm? Could be also no reaction, but no duration or consumption is okay because it's actually like we can it's setting on the problem. So no generation or consumption. I don't want to write it incorrectly. I sometimes do that a lot in my notes when I'm doing it quickly. And so okay. So that based on the problem, that's two things that we can say. We could also talk about what I was talking here about the conservation of mass, which is like we know that the mass coming in the stream one is going to be equal to the mass coming out from stream two, stream three, and stream four. That's not something that you have to say necessarily, but I always like to state that, and we know this. We know this based on the fact that D2 is equal to D3 equal to D4, the diameters. That's essentially what we know it. And another thing that we can say from this is that M2 is equal to M3, which is equal to M4, or are relatively similar. We're essentially saying that the mass that's going out is the same in each stream, and that their addition is going to be equal to the input. Awesome. So now let's go for question 4. Circle the answer in each column that best describes the system, okay? So let's go, open or close. So we know that a closed system is a system that doesn't have any exchange. In this case, we do have an exchange where getting some output and getting some input. So therefore, we know for a fact that it's gonna be open, right? Then we have this, when I was creating this, pretty sure you saw it this way. So each of them is a column. When I got the PDF, I mean this PDF I set up, my bad. There shouldn't be any differences from now on. So we know one of the assumptions, and also stated here, that the actual system is a steady state. So we can definitely say that. Something from the above that we realize is that a time is not stated. And it's kind of like, and I was talking to some teams during the quiz about like, oh yeah, what about if we just assume the time is the time filling up the bottle? I mean, that's something you can think about, but based on the constraints of the problem, there's no time stated anywhere. So as I say always, try to do it as simple as possible with a question there the problem is asking you, and try to restrain yourself to information you're given. If you're asked to get more information or to add more assumptions or to do that, do so. But by thinking that way, you can definitely go for a different complete route and lose some points. So based on the fact that we don't have a definite time, it's continuous, right? Awesome. Continuous because the time was not stated. And since the insulin is not reacting, it's not generated, not consumed, we can definitely say that it's not reacting. There's no reaction. Okay, awesome. Question 4, done. Okay, should algebraic differential integral equation be used to describe the system, and why? So based on the fact that we are not in a discrete time point, we can cross uh, I just read it, but I'm trying to say it, but I'm gonna read it again. We can cross an integral, because an integral is based on a differential parameters. You have a certain time and you get a value, Like for example, if you got velocity, you integrate it, you're gonna get distance. In this case, we don't have that. We don't have that time frame. So integral it's not going to advance. The same with algebraic. In algebraic, you're like adding or subtracting stuff based on a specific quantities or time. But in this case, since this process continues, we are not able to do that either. Therefore, we can say that it's differential. So what I'm gonna suggest you is like by doing that, we can say here that it's differential and or because or due to the fact, whatever you would like to say, the problem or the time, I'm sorry, the time is not stated in the problem. Stated or specified. Great. Are the following conserved in the system? So given that there's not reaction, that like insulin is not being like consumed, it's not disappearing like into another product, and the fact that we know the conservation of mass, like everything going in is going out, we can safely say that no, we can safely say that yes, the mass of insulin is conserved because there's not urination or consumption of insulin. So yes, it's conserved. Yes, conserved. Conserved. Said why? We said that there's not generation. There's not generation or consumption. Consumption. Okay. And something that we can safely say due to thermodynamics is that the total mass is always conserved. We're not dealing with weird atomic like weapons or anything like that will destroy matter or something like that. So yes, always concerned. Always conserved. All right, we did 6. 7. Write a reduced mass accounting equation. Okay, so when we're talking about reduce, it's not the whole thing. So when I said the whole thing, it's this. So whole thing, whole like general. So we have mass in minus mass out is equal to, mass generated minus mass consumed is equal to mass or system accumulation. So something that is key here, and you can definitely lose points if you don't read this correctly, is that it says mass. We're not talking about tridents here because that's when we are talking about general case, we're talking about mass. So everything has to do with mass. Another thing that I forgot to do here is that we were said that we are talking in differential. So therefore we have to add a dot describing that we are talking about a differential time. This is a differential mass, mass differentiated with respect to time. That's what I tried to say. So that's the general, but that's not what they're asking us. But we can start working with it. So mass n, we know that is mass 1. So we can definitely put here mass 1 differentiate. The mass out is not only one term, it's actually 3. So we can say that mass 1 minus mass 2 minus mass 3 minus mass 4, which is what we have here, 2, 3, and 4, the output streams, that's the mass out. We know for a fact that there's not generation and there's not consumption. And we know that since the equilibrium, the system is in steady state, which is important, we know that there's not accumulation of any kind. So all of this are equal to 0. So our final reduce is going to be N1, which is the mass 1, which is the input stream minus the 3 output streams. All right? You can say it like that. You could also like say that mass 1 is equal to mass 2 plus mass 3 plus mass 4, like just like mass 1 is equal to mass 2 plus mass 3 plus mass 4. That's also okay. And you could even say, given the fact that it's only talking about the reduce, is that, let me quickly do this. So this is correct. These are possible. This is correct. This is also correct. And the other one that you can say is that mass, so getting from here, mass in minus mass out is equal to 0, which is also the reduced mass accounting equation, okay? Those three are correct. You can say the three or choose one, whatever makes you happy, okay? Awesome, okay. 7 done. Let's go for 8. So calculate the volumetric flow rate. I don't remember how to calculate it, but thankfully we have a formula sheet right here. So we know, right here, we know volumetric flow rate. What's that? That's the volume over time. Now, volume over time is, we can think of it as the velocity times the area. So the velocity that's going through the, like the velocity the liquid is going, in this case the insulin, times the area it's going through. So we know that we actually have the velocity for V1 for the input stream, and we also know the area, or we can calculate the area based on the diameter, okay? So we're gonna use this. We could also use, if we had the mass flow rate, we could also use the mass flow rate divided by the density, but we don't have that. So let me write it here quickly. So that would be 8. So for the volumetric flow rate, we need velocity 1 times the area 1. And we know that velocity 1 is 50 centimeters and the diameter is 2 millimeters. So for the velocity 1, it's going to be, let me put it here, 50? Yeah, 50. 50 centimeters over second times, also another important thing, a millimeter is not the same as a centimeter. So if you do your math and the units are not correct, you might not get the right answer. So we know that 2 millimeters is equal to 0.2 centimeters. So that will be 0.2 centimeters. The same with this. All this will be equal to 0.5 centimeters, just to state that, okay? So we're gonna multiply by the area. What's the area here? We're talking about stream. So we're talking about cylinders. So a cylinder, the cross-sectional area is a circle. So what's the area of a circle? Pi r squared. But we have the diameter, not a problem. We can do the following. So pi diameter squared divided by 2 squared. So essentially is pi diameter divided by 4, diameter 1. And we know that the diameter 1 is 0.2 centimeters. What's that? Yeah, 0.2 centimeters. Okay. Here. Okay. So let me get my handy calculator. Do this really quickly. So I love decimals, so that's the reason I have it here. So 50 times pi. Oh, here's pi divided by 4 times, we said, let's put a parenthesis, 0.2 squared. And we close parentheses, and the answer is, for the volumetric flow rate, 1, right? Well, the total volumetric flow rate incoming to stream, yeah. So that's gonna be equal to whatever we have here, which is 1.57 sig fig. Usually like having two decimals is a good practice. And what are the units? So we have centimeters squared here, and then we have 1 centimeter, so centimeters cubed divided by seconds. Okay, but I think that's not the final answer. Let me check. Why? In terms of numerical answer, that's the final answer, but we are talking about millimeters over seconds. You have to know that centimeter cubed, it's equal to milliliter. It's equal to milliliter. Sorry, not milli, whatever I said before. That's wrong. Okay. And our final answer. Oh, we can do that here. It's going to be, can add that factor here. So 1 cubic centimeter, it's equal to 1 milliliter. So we can cancel out the centimeters. So we get that the volume, the incoming volume is 1.57 milliliters over second. That's our final answer. Let's box it. Awesome. Don't forget to box your numerical, at least your numerical answers. The rest, if it's words or anything else, it's okay. But if you're talking about a numerical answer, box it, because that's, yeah, you're gonna get points off if you don't box your final answer. Okay. All right, we're almost ready. I think the last question is 11, so we're killing it here. Okay, 9. Calculate the total mass flow rate. Okay, in each of the 3 output streams. So since we know that the output mass flow rate is like a third of the input, we can calculate the mass flow rate of the input, like the stream that is coming in. So, like we have. Oh, I didn't know I could do that. No, that wasn't that good. Oh well, we can. So we can calculate we know that there's a relationship based on the conservation equations right here, that the mass coming in is equal to the mass coming out. So M1 is equal to M2, M3, M4. And we know that they're the same. So we can do is calculate the mass flow rate of M1 and then divide that by 3. And therefore we can get the output of one stream. And since all streams are the same, by that you can calculate, you can state your final answer of whatever grams over seconds we get for your final answer. What I want to point out here is you can do this before, like starting doing calculations, start thinking about, okay, how can I approach this? What can I do? That kind of thing. Okay. So let's talk about the first step. The first step is we set to calculate the mass of any flowing liquid. We already have the flow rate one. So let's see, we want to calculate mass flow rate 1, the input. Let's see what questions we have. So mass flow rate. So I'm pretty sure we have the density. So with the density times the volumetric flow rate, we can calculate the mass flow rate. So we only need the density. So it's right here. So mass flow rate 1 is going to be equal to the volumetric flow rate 1 times the density. I'm pretty sure it's 1.2 something. Yeah, 1.2 grams over milliliter. Great. So we just work that out. So it's going to be equals to 1.57 times milliliters over second times, we said 1.2 grams over second. Oh, over milliliters. I was like, what? That's the density, it's not in time. I'm sorry. Also, what I'm trying to say is that it's okay if you commit a mistake, only try to double check, and if something doesn't feel right, try to get to the bottom of it. So we get this, and the final answer for the input. Remember, it's not our final answer, but it's the construction. It's going to be 1.57. Oops. Let me erase that. 1.57 times 1.2. So we get that the inflowing mass is 1.88 oops 88 uh, grams. Something that I we should do, or you'll try to do, or you could do, just to be more precise, is to try, if you can, have something like I have here, or in your calculator, use this number, like whatever this is, like not like the entire decimal. That's what I'm trying to say, because if you compare the answer that I'm getting in both instances, we can see that, oh yeah, we get the same. Okay, well, 1.88. I think the answer key is a little different, but we're gonna go from 1.88. Shouldn't be that big of a deal. Okay. And we have 1.88 grams over seconds. Okay. So we know that. The second thing that I was talking about is that M1 is equal to M2 plus M3 plus M4. Okay. So since all these are equal, or we can say that M out is equal to M1, which is equal to M2, M3, and M4, we can say that M1, like the input stream, is going to be equal to 3 times M out. Okay? And then we can divide M input by 3. I'm going to get, don't forget the points, M out, which is what we're trying to look for here. So M out will be whatever we got divided by 3. Okay, let me get my calculator again. Let's divide that by 3, oops, 3. Let's see what we get here. Same thing, I suppose. Yeah, 0.628. So 0.63. Okay. So if we can say that M out is equal to 0.69. We want, oh, no, 63. Oops, my bad. 63, no 69. 63 grams over second, which is this. I think I should write it. Let me write it. So, and one, we said is 1.88 grams per second divided by 3 is equal to M out. What I'm trying to do here and showcase is that I know that there's math that you can do in your head, and just you feel like you can actually put the answer, but I would advise you to add as much detail as you can. So the final answer should be 0.63 grams per second is equal to M out. That's the final answer. Okay? Don't forget to box it. Did I have it like really tiny here? Oh, okay. That might work. Okay. Awesome. So let me box it because we don't want to forget that. Okay, moving on. Ready did question 9. Let's go for question 10. What does it say? So now we're in a different scenario. Let's see what it says. So your supervisor one. Oh, I'm gonna be here because my neck hurts a little bit. Your supervisor wants you to verify that the parameters of the fill station were established correctly. More specifically, she wants you to verify that the velocity if the input stream is adequate, not too fast or not too slow. So we want to know if it's adequate or not. Okay, you collect additional information from the technicians working on the station. Something that I don't have here that you did have in your quiz, it's that normally the motion of the vial, it's like 1 second. So let's say, well, I can definitely do it here. Let's say you're in a production line. Okay, then you have like a set of 3 vials over here. Then you have your machine that it's like letting some insulin in the vials. And then this guys move forward to here when they're like already filled. And they, like a new set of vials goes here again and they get filled. So this process right here is 1 second. So vial movement, just 1 second. That's something that, trust me, we're gonna need it in the future, but let's keep going. Okay. The mass fraction of insulin in the output stream is 0.2. Okay, so whatever the mass is, multiply by 20%, and that's we're gonna get the final mass. So the final volume of each vial is 5 milliliters. Okay, that's important. That's the final volume. So volume, the mass fraction of insulin, the desired concentration of insulin is this one. Okay. And calculate the mass flow rate of insulin. Okay. So in that case, we're talking about the output stream. Okay, so we can go M out, which already calculated, which is 0.63, I think. Yep. Well, so M out is equal to 0.63 grams over second. But M insulin, or M out insulin, better said, out insulin is going to be equal to that number, whatever the mass was, times the mass fraction. So 20% of that. So if we go here, can do it really quickly. Let's see, 0.628 times 0.2, get 0.126. Okay, we're gonna stay here. So the mass out of insulin is 0.126 grams over second. That's what we're asked. Yeah, that's what we asked exactly, which is the mass output of insulin. Okay, so we're gonna box this numerical answer. Great. Let's keep going. Okay, so final question. How much time would it take to fill up 1 vial? To achieve the desired insulin concentration, so you have to use concentration, the vial volume, maybe the mass going out. Okay. Based on that information, we recommend increasing, decreasing, or maintaining the input velocity. So, okay, so we know, what do we know? So we know that mass of the vial should be the concentration, at least the insulin, like the amount of insulin in that vial. It's going to be the concentration that we have, which I think is 2 milligrams per milliliter, times the volume. That's what we're gonna get mass. So let's start with that. So the mass of the vial, or the mass of insulin in the vial, is going to be equal to 5 milliliters times 2 milligrams over milliliters. So here we're gonna get, we don't need the calculator for this, it's gonna be 10 milligrams. But based on the concentrations, well, not concentration, but in other parameters like the mass out, we want to get this into grams. So 1 milligram, it's like a thousandth of a gram. So what I know, it's that like 10 grams is 0.01 grams. So I think it's 10 divided by 1,000. Yeah, okay. So we know that 1 milligram, well, 1 gram is equal to 1,000 milli, which is 1,000 milligrams. So if we want to go to grams, we go 1 gram. No, oops. 1 gram, there you go. 1,000 milligrams. So we get 0.01, 0.01. Well, you can do that with this with your head, but usually something that happens to me quite a bit is that I move one, like the period one way of the other, and that messes up the entire answer. So if you're like me, you can double check, okay? Awesome. So I already know the mass. And we know that the definition of mass flow rate is it's going to be equal to the mass divided by the time, right? So if we already know the mass, which is 0.02 grams, and we already know the mass flow rate, which is 0.12, wow, okay. We can calculate the time. So let's do that. So time, well, so the time here is going to be time is equal to mass divided by the flow rate. Okay. So from here, we know time to fill is going to be equal to the mass out of insulin, like the desired amount of insulin that we have to, that we want in the vial, divided by the, I'm sorry, the insulin that we calculated here, which is, we call it M vial of insulin, divided by the mass flow rate out that we calculated previously of insulin. That's how I call it. Insulin. And it's going to be equal to 0.01 grams divided by 0.12. Oops. Uh-oh. There you go. 0.126 grams over seconds. Yes. Seconds. So let's do that really quick. That's 0.01 divided by 0.126. Well, it's a tiny, tiny, tiny number. Tiny number. It's a very tiny, tiny number. So we have to go again to a question, because that's an numeric answer, but we have to say if we should like increase, decrease, or maintain the input velocity. So in this case, since the time to fill It's so low, so fast. I personally, to be more efficient, because I will decrease it. And let's think it this way. Mind your Starbucks, and they're in your car, you're driving, and there's a line. And it takes you from where you ask for your food to whatever you get your food. Well, this, I think, more to McDonald's, but you're in a drive-through. You're getting your order. I want this price, and then in the next like window, you're gonna get your food. What it's saying here is that, for example, it takes you 1 second in this sample to get to the next window from when you ask, but it takes 0.08 seconds to make the food and deliver it to you. So after they delivered, in this case, which is, since it's a liquid, they're like releasing the food. So the time that takes me from here to there, to from the first window where I asked for my food to the second window, which is 1 second, there's so much food being wasted because they're getting my food ready and they're throwing it away. Getting my food ready, throwing it away. So when I get there, I receive the food, which is the same thing that it's happening. So we have a production line, and in this production line, we have a new vial, and we have, well, there are actually three. And this output. So it takes 1 second to get there, right? That while that second is taking, like this machine over here is still like squirting insulin. Therefore, what I would say is the following. The time is very fast. And a lot of material, aka insulin, is wasted. Would decrease the speed quite a bit. So it matches the, how can I say it, production line. Well, that's it. We just did quiz one. Oh, don't forget, I forgot. Let's put Juan Martinez. That's my name. And signature. That's my signature, so you guys can see it. Yeah, you can't forget to do that. This right here, like, wouldn't be graded, but I'm pretty sure you should not have a problem if you, like me, you start like writing somewhere before to get your thoughts and everything. So yeah, that's quiz one, everybody. Thank you so much for watching, and see you next quiz. Bye.